Austin, Texas. And there's a slide coming up that shows all of the taps. And if we're on the first slide, and I apologize, first I have to explain I'm traveling and had difficulty getting the hot spot set up. And I don't know why I can't do it, but now Ellie and I are working in close coordination here to give you this presentation today. So this is combined heat and power, CHP portion of it, of the TAP. The other TAP stands for Technical Assistance Partnership. So this is a program from the Department of Energy, and it's the Office of Advanced Manufacturing. And I always like to tell the audience, that, particularly if it's companies or utilities, others that we help out on these on the CHP program, that it's free. Although, and I don't know how many of you are out there in the working world yet, but if you do work, it's all paid for by taxes. So all of us work and contribute our tax dollars to this program. So it's free, but it is paid for by everyone. So combined heat and power, CHP, and related applications for resilience, reliability, and reduced operating costs. These are key attributes of the program that we like to focus on, because these are key attributes of businesses, profit or nonprofit, that have operating costs one way or the other. And this is what we help to reduce, are these operating costs, and improve resilience and reliability. Next slide. One agenda, the agenda slide. There you go. So what we'll talk about today is a quick review of the program. A not so quick review. We'll dig in a little bit more on the CHP, the technology, since I understand that we're all engineers here. Microgrids and resilience, and then kind of a quick overview of the finances, the cost side of it, and some case studies. We have some applications, but I was not able to find a case study in particular on breweries. I don't know if that's of interest to specifically to this crowd, but typically with university students, that's a good application to talk about. Next slide, please. So where are we at, and what do we do? Primarily, it's we call it end user engagement. You would consider this to be the owners of facilities that are going to put this in, or universities such as U of U. Stakeholders, we try to engage stakeholders, which would be others that are interested in CHP. Gas utilities are a great partner of ours, because if an end user puts in a CHP system, he's going to use more gas and less electricity from utility companies, because he's making his own electricity. So that makes the gas utility companies a stakeholder and an enthusiast and cheerleader for us to work with. Other stakeholders are, for example, engineering companies who can do business with end users, designing systems, and construction companies who obviously will build a system for it. And then other technical services that we provide, and we'll talk about that later, but that is the support that we can provide to you, either at the university or in the future when you've entered the workforce and are working for companies that, or you have your own company that is developing CHP systems. We can provide, again, this free support service for you. Next slide. And I'm kind of rushing through because this is typically as a minimum of 1 hour briefing, and we're going to try to do it in about 45 or so. And also I've mentioned that If there are questions, Ellie, since you're the only one I can see, if you just wave your hand a little bit, I'll know to stop and take questions. And please feel free to ask questions through throughout the briefing. So CHP TAPS, Combined Heat and Power Technical Assistance Partnership. I'll just say that the words for the last time, CHP TAP though. That's what we'll refer to it. We have 10 regions across the country, and these mimic the EPA regions. So these 10 regions are the same as the 10 EPA regions. I am in the 2 purple ones. These are the South Central and Upper West, and of course Utah, you see there in the Upper West. We support, our group is based out of Houston. I mentioned I'm out of Austin, Texas, but we support those groups that I mentioned on the previous slide, end users and stakeholders throughout those states. And there's our contact information. Next slide, please. CHP today in the United States. Well, the pie chart on the left, basic categories of where it's being applied, and in terms of capacity, gigawatts of power, and correspondingly, relatively speaking, the same amount of BTUs of thermal energy, both hot commodities and cold cooling commodities. So you can see what you would expect to be the normal type of distribution here: chemical plants, refineries, pulp and paper, where there are large energy thermal loads. Use steam and or hot water are the primary categories, but all these others, more or less, according to the pie chart there, categories of industry and applications that can benefit from CHP. And next slide, 6. What are the benefits of CHP? Well, it's more efficient from an energy standpoint, and then separate generation of electricity, particularly from a remote power plant, and more efficient with respect to heating and cooling, because we use the waste heat from whatever the prime mover is, and I'll call it an engine, and because typically it's a reciprocating piston engine or a turbine, combustion turbine type engine that we see, and typically going to be burning natural gas or biogases of some sort. So it's more efficient as a process, as a thermal process, energy process. Higher efficiency translates to lower operating costs. And this is key to the majority, vast majority, I'd say 99% of the applications that we're involved in. Maybe not that much anymore, because reliability is coming into it and resilience as key factors for decisions of doing it, but of installing a CHP system. But it has to have associated benefits economically, financially. So the way that that's manifested for a business is through lower operating costs. So CHP is more efficient, and that translates into lower operating costs. Also reduces emissions of pollutants per BTU of thermal product, as well as per kilowatt hour of electricity. It's more efficient. And it increases energy reliability and energy resilience. And this is a basic tenet of all distributed generation, whether it's energy distribution or the computing power distribution. One of the great examples I like to use of how distributed generation and CHP has come into vogue lately is lately being, say, in the last 25, 30 years, is very similar to the computer industry, where started out with large mainframes, which would be similar to our large central stations, big power plants, and then evolved into desktop machines distributed, where folks had that computing power at their location, which would translate to large boilers and then taking the waste heat from that and turning a steam turbine generator, and then into what we have today of laptops, which are distributed, and even our cell phones. And this translates more directly into the systems that are put in at, for example, commercial buildings, not smaller yet than what is in, for example, at universities or large industrial facilities or um, district energy systems. So it's more distributed than that. So it's a very close correlation between how the computing power has been distributed throughout the user side of the equation, where the same has occurred with power and thermal energy distribution being going out into the end user, if you will, the buildings, and distributed throughout the grid. Next slide, please. So from a process standpoint, distributed generation, in particular CHP, more efficient. It's good that we have engineers. You understand what this block diagram on the right is actually showing us. And the traditional system, if you will, for energy supply to, for example, a process facility, a manufacturing facility, they're taking power from the grid, which is generated by a power plant some distance away. The power goes through step-up transformers, goes cross country, and comes down to a distribution system through step-down transformers, and then from that distribution system to the end user through, again, another round of step-down transformers, so that by the time it gets to the end user, it's somewhere in the low 30% efficiency. And then that end user, if he has a thermal load, he's got boilers at his facility, which are potentially very highly efficient. But when we look at the block on the green block, CHP block on the right, when we combine the very high efficiency boiler with the very low efficiency power plant miles away, the CHP system is going to use upwards of 75 to 80, 85% less of the fuel that the power plants and boilers will use. So it's in that range of 75% to 80, 85%, where the system coming in is something like 50% maybe, or less, depending on how big the boilers are, how old they are, how much benefit comes out of that. But the electric power is always going to be in that low 30% efficiency. So the use of our natural resources to generate it is not as well used, not as efficiently converted to the energy source that is used by the end user. Next slide, please. A little more diagrammatic, schematic, if you will, of the CHP system. On the left, the yellow box represents whatever type of fuel is going into the white box, which is a prime mover. And then the blue box comes out of that, a shaft drive turning a generator, which then makes the big blue box the electricity. The prime mover is using some type of fuel and combusting it and creating heat, which is captured rather than just going off as waste heat off into the environment. It's captured in a heat exchanger, and that heat exchanger has on its secondary side created either hot water, steam, or it could be hot water or steam used in an absorption chiller and making cooling product, either for space cooling, refrigeration, dehumidification. So that's kind of the schematic of what we looked at on the previous slide. And next. What are common CHP technologies? This is really more in terms of the prime mover. And this is a non-linear scale. So if you look at the scale on the x-axis, you'll see it goes from 50 kilowatts to 100 kilowatts to 1 megawatt and then to 10 megawatts. So obviously non-linear, but it's good to be able to depict these different types of prime movers. And I'm going to start in the middle with reciprocating engines, the orange chevron there or arrow. And the reason is that it is the most broadly applied in terms of capability and capacity, and also simply in terms of numbers of systems installed. This is by far the most common type of prime mover, reciprocating piston engine in applications of CHP. And you can see the size range. And that's a good reason why from 50 kilowatts, from the lowest up to 10 megawatts, and that's per prime mover. So if you have a 10 megawatt engine and you want to put in, say, 50 megawatts of capacity, it's a very good model to use 5 10 megawatt recip piston engines, or 10 5 megawatt machines, or sometimes even more than that. The nice thing about putting multiple generator or prime mover generator sets in is that you have some somewhat of built-in redundancy, particularly if your load curve is not flat. So piston engines, recip piston engines, most common application. Next would be up in the turbine types, both microturbine and gas turbine, and you can see kind of a general depiction of the size ranges that are available in that. And gas turbines go upwards to 200-300 per engine. And then on the bottom, fuel cells are not broadly, don't have a broad range of capacity. Also very expensive, not really a financially viable solution at this point. Any questions on the prime movers here, on the types? Okay.
Daryl, I'll just chime in and say that for most of the applications that we look at here at the University of Utah's IAC, we're typically in that gas turbine range, just for context for everyone.
Oh, larger systems, I take it then. Is that correct? The larger systems, like upwards of
yes, correct. Yeah. Mm-hmm.
20, 30, 40 megawatts? Okay, good, very good. I mentioned that we can take the hot waste heat and actually create cooling. And since you're all engineers, you probably understand the two-phase, the properties of two-phase materials, for example, lithium bromide, and how to use that in an absorber. And this is a technology that has come quite a ways in terms of reliability and simplicity in the last decade. Absorption chillers were typically not broadly applied, not well understood, hard to find technicians and service maintenance people for them. They tended to quote freeze up, which just means the lithium bromide gets hardened up inside of it for whatever reason in proper operation. But they have become much more reliable, like I say, in the last 10 years or so, 10, 15 years even, and are beginning to see more broad application in industry. Very good system or component within a system to provide chilling. And this is, I would say York is probably in the US one of the best suppliers of the larger systems of this. Next slide. What is a microgrid? Microgrid is to some extent a kind of a bannered, marketed power distribution system, what was typically known as a power distribution system. The difference being that a microgrid can operate both connected and disconnected from the grid. And typically you're going to want to be connected to the grid just because of the cost of doing a high reliability disconnected system. The grid is relatively reliable in the US, you know, in the mid to upper 90% reliability level. And it has, particularly off peak, a lot of cheap power on it, all the way down to zero cost for kilowatt hours for upwards of a couple hundred hours a year across the country in you know, the 12 to 12 p.m., 12 a.m. to 4 a.m. time range. So it's typically more economically, financially viable to stay connected to the grid and take advantage of that power. But when the grid goes down, the microgrid needs to operate on its own. And even when the grid is up, the microgrid operating independently, if you will, from a control standpoint, might want to enable various power sources on it, capacity types, just because it's cheaper even during the day to make your own power, if you will, and also because it's more reliable, cleaner power. So what is a microgrid? This is a great little diagram of it, kind of a semi-electrical schematic. If we look at on the left-hand side, there's a circle that says PCC, point of common coupling. That's where the microgrid on the left there connects to the main grid. And then on the right, a nice little caricature, if you will, of a microgrid system. And microgrids, basically, any microgrid has three basic components. It has loads, it has capacity generation, and it has interconnection of those two with bidirectional flow of both power and communication, or I should say, yeah, power, energy, and communication. So it's bidirectional. In other words, particularly from a control standpoint, it's not just buildings and loads that are telling the grid how much power they need, but it could be the grid telling these microgrids, well, I need some power, I need some capacity, and pulling and reversing the flow and generating the microgrid generating more power than it's using. So it's bi-directional flow of power, but it takes bi-directional flow of communication of controls to be able to coordinate that bidirectional flow of power. You have to have that point of common coupling to be not just electrical, but also the controls of it. So three things that comprise a microgrid: loads, capacity, and bidirectional flow of power and communication. Next slide, please. Well, is there any questions on it? Because microgrids are quite the buzz these days. And I might also mention that I was fortunate enough about 6 years ago now to receive be awarded a patent in microgrid development. It's called Secure Microgrid. And if you want to look that up, it'll give a really detailed electrical explanation of something I have a hard time explaining, but would certainly like the opportunity to discuss that with anyone if you're interested. Okay, so, and I'll go pretty quick on this slide. CHP can enable other microgrid technologies. Well, it's basically, you've got this power distribution system that has a variety of sources of capacity, which different types of capacity have different value propositions, if you will, to the grid. A big recip engine or a combustion turbine, very clean power, very robust, has a good volt var frequency maintenance for the grid. It's rock solid, but it can take some time to respond to the grid needs. A battery, an inverter-based system, not synchronous without a signal, but it can respond very, very quickly, but typically for a shorter period of time. Basically however how many megawatt hours, kilowatt hours even that the battery has in terms of capacity. It's not typically going to be anywhere near what a combustion engine will be able to provide in terms of duration. So different, I call value propositions to the grid, to the owners of microgrids to determine what the actual financial benefits are from having it. Next slide, please. Resilience versus reliability. I'm going to start with reliability first. That's a real easy and common and long-term defined term, if you will. Reliability. It's how it's performance over time, and it's a percentage straight up. Resilience is performance over a longer period of time, but it could be any level of performance, whereas reliability is typically at some specified level of performance over some period of time, a year or 6 months. Resilience is more, and I'll use the example of a boxer. I used to box, and we used to talk about a guy, and typically it's going to be, when I was doing this 100 years ago, it's guys boxing. So I want to stay correct on that. It's the person boxing. At any rate, when the term was, had a glass nose. So if you punch them in the nose, fall down, pass out. However, resilience is, in my analogy, a boxer who can take a hit and maybe be phased and staggered a little bit. Maybe he goes down, takes an 8 count, but he can get back up. Or maybe he takes a long 8 count and is out of it can't box that time, but he comes back to box the next day. So resilience, in terms correlating that to power systems, is a system loses some generation and it has a voltage dip or a frequency sag. I think I use those terms backwards, but at any rate, it comes back. It lasts a few seconds and it comes back. Or maybe there's a short somewhere in the system and a breaker throws, but it resets in 8 seconds. That's a resilient system. It's coming back. Or maybe there's an outage, a piece in a portion of a distribution system goes down, but it's able to be rerouted around and it takes a couple minutes. Or another level of resilience would be a storm goes through and it takes down poles and the system goes down, but the utility has placed poles in pre-positioned them where they know that they have a weaker portion or vulnerable portion of the system, and within 24 hours they've got poles and wires back up. Those are examples of resilience in terms of a system providing its power over a period of time, but it's not that it's at 100% of the capacity or the rated capacity. So resilience is similar to, but different than reliability. And I should take any questions at this point because it's a It's a fairly new concept that's really taken over in the, not just the power industry, but almost common vernacular, resilience. Does that make sense to everyone? Okay. So how does CHP increase resilience? Well, again, I'll come back to the example of the distributed generation, and we're breaking up the power generators to multiple generators that then have um, independence from each other. And when one goes down, one part of a system goes down, it doesn't take the whole system down. So for end users, provides CHP can provide continuous supply of electricity and thermal energy for critical loads during storms, whenever it needs to go, for example, into island mode operation. It can start up and operate without the grid. It can withstand long multi-day utility grid outages. You know, if it's a system that has fuel storage on site or not, that could provide longer term operation. And I'm noticing the time, I'm going to have to skip through some of this. You can read through these, but resilience, I'm going now to the the next slide on it. CHP proven to be resilient in various hurricane scenarios. What are the benefits of CHP? I'm on slide 16, Ellie. One more, there we go. I'm just going to touch on these quickly again. More efficient. That means lower operating costs, reduced emissions, and then the characteristics that we just discussed about resilience and reliability. Slide 17, total CHP by application, background material. Next slide. Where is it used? Nationwide, particularly on the coast, for a couple of reasons. One, that's where electricity is probably the highest priced throughout the nation. We have high population densities, high electric loads, high cost. Also storms, weather storms along the coast make those systems more vulnerable. The grid's more vulnerable, which makes CHP more valuable. The money question. What does it cost and who's going to pay for it? This is a very busy slide here, slide 20. And I'm just going to go to the bottom line and say that from left to right, smaller to bigger systems, you can see the cost per kilowatt hour. In other words, the cost per size. Size is important for cost savings. There's a lot of scaling benefits to it. A couple of examples. How can the CHP system be financed? You can have the utility, the regulated utility could own it and generate, and here's an example. The next slide is a for-profit business can be the end user owned, or the next slide could be third party owned. And basically third party owned would be what are known as energy service agreements, ESAs, that a third party will come in who specializes in power systems for a bowling alley, for example, who might want to put a CHP system in and it works out financially, but they don't want to operate it and maintain it. So they would have a third party come and put it in, charge them for the thermal and electric product, and use the difference in cost for making it yourself and what the facility would pay the utility to pay for it. So third party ownership. Energy as a service in CHP. What are the best candidates? Large and constant thermal loads. And every other one of these could be large and constant thermal load. That's the biggest requirement typically, as well as then um, high reliability or improved resilience. Those are key factors. Next slide, 25. Working with CHP Tap, we provide support. We can help you on slide 26 with screening, the technical assistance of feasibility analysis. We can review these when they're done by others. We can't compete with industry, but this upfront analysis and then support into the reviews of IGAs, the investment grade analyses, pro formas, all of the components of feasibility study. And then we can help with reviewing technical specifications and bids. And slide 27 is an output from one of our very high level screening pro forma analyses. And the bottom line on that is a simple payback period in terms of years. And case studies, some universities. I'll let you, y'all can study these or review these on your own. And these have all been exercised, if you will, lately by storms, particularly Galveston, with the last two hurricanes coming through Houston area. This CHP system, that they actually put a wall around the facility. You can see it there, a concrete wall to keep the water out, but it continued to operate when others did, the rest of the island was dark. Case study. Would like to see if you all have one. We can get a system put in and get another case study. Slide 32. As most government agencies, we have a website that has myriad of rabbit holes to go down. When you do need resources, please just contact me. If you need reference information, really that's the best, is to contact me. And working one-on-one is the most efficient use of your time and the most productive use of these various resources we generated. If our resources can be used more efficiently and you can make more effective use of your time, that's good for everybody. 33 is more project resources. Project resources. Next step, slide 35. As I mentioned, contact me, contact others. I'll put you in touch with others in our TAP for wherever the specialties might of skills and experience might lie. But it's the one-on-one direct support for your CHP evaluations that we'll both realize the most benefit from. Really need to work, use our experience. I've done this for years. I was a developer and put systems in that if they didn't operate, I didn't put food on the table. So there's nothing more demanding than to confirm a system that's going to work, then you're dependent on it for your income. Engage with us, bottom line. So summary, CHP is proven technology. It's not the bloody tip of the spear. It's well proven, well sorted out. It takes creative, and the fun part of it is creative solutions from a clean sheet of paper. There are new drivers like resilience that are creating new opportunities for CHP. And there you see it again, engage with us. Please contact me or others in the TAP. We're here to help. It's one of those few times where you can say I'm from the government and I'm here to help, and it actually has some credibility to it. And it's 6 o'clock.
Awesome. Yeah, nice job, Daryl. You got through it. I'm impressed.
Well, hopefully there's some amount of it was absorbed. That's the most important thing.
And we got it recorded, so we'll always have that chance to go back. So we definitely appreciate your time today. Daryl, I'm gonna just for our groups benefit before we say goodnight for this session. I want to reinforce just a couple of things that you said for everyone to take away. First of all, the like Daryl said, the key for CHP applications is some kind of constant or continuous heat or thermal load. So for the assessments, especially that have manufacturing processes that use heat, it's always worth taking a look at CHP applications. And if you do have that opportunity, Daryl gave you a lot of information today, including his contact information. I can always also connect the assessment teams with CHP Taps to get the information and resources that Daryl's gone through here. So those are the two things I want you all, want the group to keep in mind for future CHP opportunities. Daryl, thanks again. And I'll just say to the rest of the group, good luck with your finals. Enjoy your holidays if I don't see you before that, but I hope to see you all tomorrow night at our team celebration. So thanks again. Good night.
Good night.